In the last video, we took a look at this definition of what it meant to take the limit of a vector-valued function. And there was a lot of detail there, but again, the most important thing to take away from it is that the output of a limit for a vector-valued function is a vector. And so we're going to try to see here in this video a couple different things that kind of follow from that definition. And they're going to be related to ultimately concepts again that we've talked about within a Calc 1 class. So let's take a look here. Let's suppose I have a vector valued function here like r of t, and these are all of its component functions. So there's some formulas there to get the x, the y, and the z components. Well, if I wanted to go ahead and calculate the limit of my vector valued function, I actually wanted to compute it and figure out what the final resulting vector would be, I actually end up with the following. The limit of my r of t as t approaches a can actually be calculated really simply, and this is really great. I just actually have to go calculate three individual limits, specifically the limits of my three component functions. So I have a limit here of my f of t, limit of the g of t, and finally a limit of the h of t. So this is great news. This actually means that although we had kind of a weird definition of what this limit represented in the last video, the actual algebraic calculations and things like that we have to do are things we're very familiar with. To calculate the limit of a vector valued function, I just have to kind of do three individual Calc 1 limits, one for each of the components. Okay, there's a couple other things though that we should make note of here. Okay? First off, an important definition. We've talked about in a Calc 1 class what it meant for functions to be continuous. So I'll write here, in Calc 1, we had a definition that a function was going to be continuous if it was the case that the limit of that function as x approached a was equal to f of a. Essentially, this was the concept that wherever my path actually leads me, right? If I have a function f of x, and the limit's going to ask, where does the path lead me? To what y value? As long as the actual y value of the graph is at the same spot that the limit or the path is leading me to, then I would say that my graph is continuous. So this meant that functions were continuous if they didn't have like holes or gaps or jumps or breaks or like vertical asymptotes or other weird things like that going on. And of course, functions that did have things like that, maybe say a function like this, would be considered not a continuous function, whereas this one over here would be. So we're going to be trying to think about the same sort of idea in a vector function sort of scenario, where I'm not just dealing with functions in 2 space, but I'm dealing with functions in 3 space. But again, if I want this function to be continuous, I need to make sure there's not going to be any holes or jumps or gaps or breaks or asymptotes or anything weird happening out in 3 space. So what we'll notice is that if the following is true, that is, if I can take the limit here of r of t as t approaches a, so that's seeing where do that sequence of vectors that we saw in the last video, where do they kind of lead me to feel like I'm going to be pointing? What final point does it look like they're going to shoot out? As long as that's actually equal to r of a, that is, the actual value or the actual vector value that I end up with when I plug in a, then my function's continuous. And hopefully you see that the connection here is very strong, right? We have the same basic format. The limit of the function needs to be equal to the function evaluated at the point we were approaching. If I have something like that, then a vector valued function is going to be continuous. The nice thing here, though, is that if we look at the next theorem, we also get a really kind of valuable tool here. This theorem states that if a vector function r is continuous at a, okay, so if I have that, then that must mean that its component functions are continuous at a. So if I go back up here, if r of t is continuous at a spot, then that means each of its individual component pieces were continuous at that spot. But remember that we talked about this on our first or second day of class together, that whenever we have this sort of phrasing, if and only if, it means you can actually read the statement both forwards and backwards, kind of like flip-flop the two ends, and it should still be true. So this statement also says, if you find that the component functions are continuous at a number a, then the vector valued function will be continuous there. So it kind of operates in both directions. So this is really, really nice because it allows us to kind of use our knowledge from Calc 1 to quickly determine if a vector valued function is continuous. Instead of checking at all points, we could simply say, is f of t continuous? Is g of t continuous? Is h of t continuous? If they are, r of t must be continuous. Okay. We're going to go ahead and try to see how that would actually work here in example number 1. Let's take a look. We have a fairly complicated vector function here. I have it in the I, j, k form of a vector function. But let's see if we can answer the two following questions about it. Can I find the limit of this function as t approaches 1? Okay. Based on what we had seen up above, if I ever want to compute the limit of a vector function, what I can simply do is just calculate 3 individual limits, one for each of the components. Okay, so let's see. I can go ahead and start to calculate this out. Just saying my limit of r of t as t approaches 1 should be equal to, and I'm going to go ahead and write this in this angled bracket notation. So I need to go ahead and compute 3 different limits. So here I'll just start by setting them up, and then we'll think about how we would actually calculate them out. Okay, so I have t plus 8, and then finally, over here, need a comma. I'm going to have a limit as t approaches 1, and I have the sign of pi t over the natural log of t. Okay, so let's compute each of these limits. We'll kind of tackle them all simultaneously as we think through this. All right, remember that in Calc 1, you could always do a direct substitution as long as your function was a continuous function. So for example, if I was to take a look here at my middle component, I recognize that the square root of t plus 8 is definitely a continuous function, as long as I'm not plugging in any number for t that would cause me to take the square root of a negative. So here, calculating this y component is super easy. I'm just going to get 1 plus 8 in there, and so of course I can then easily imagine down here, I'm just going to end up with 3 for that y component. Sometimes though, when we were taking limits back in Calc 1, we weren't able to do a direct substitution. For example, take a look here. If I plugged in the value of 1 into both the numerator and denominator for t, I'm going to end up with 0 divided by 0. So that's a problem. I can't do 0 divided by 0. But that doesn't necessarily tell me anything about the limit. The limit might still exist. The limit might not exist. I have to investigate further. Never assume that because you get 0 over 0 or anything like that, that's told you whether or not the limit exists. Okay, so there's a couple ways I could approach this. One of the ways that I could approach this here would be to use some simple algebra. Okay. I could easily go ahead and say, well, I can factor a t out of the top, and what I'll then notice is that it's actually possible to cancel out a t minus 1. So I'm really just doing the limit of t. But now t is a continuous function. It doesn't have any holes or breaks or gaps or jumps or anything like that. And so the limit as I approach 1 here is just going to be 1. Okay. So calculating this limit was easy with some basic algebra. You might have also thought of a different way that I could have calculated this limit because I was getting a special form of 0 over 0. And you might recall that back in Calc 1, the way you could do this would be by using L'Hopital's rule. Now I'm actually going to go ahead and see how we would use that over here on this last limit, because you'll notice that in this limit, if I plug in a 1, my numerator does go to 0, but so does the denominator. So in this case, I would need to make use of L'Hopital's rule because there's not really any way I can algebraically simplify what I have over here like I was able to do at the left. So I'll put a little h here to indicate I'm about to use L'Hopital's rule at least on one of these 3 vectors. One of these 3 components of the vector, and we'll use it on the last guy. Remember that L'Hopital's rule said that the limit up here has an answer, But if you were to take the derivative of both the top and the bottom and put them back in place, so let's see, this would be like this, and chain rule, don't forget to multiply by the pi, then this limit and this limit must have the same answer. This was, again, as long as you had at the start the indeterminate form 0 over 0 or an infinity over some sort of infinity. All right, well, let's go ahead and quickly think about how we could evaluate this guy. Well, notice if I tried to plug in 1 now, I could actually see that the denominator is just going to be a 1, and the numerator is going to be the cosine of pi, which is -1 times pi. And so ultimately here I'm ending up with the vector of, oops, sorry, not -1, but +1, 3, and negative pi. So the limit of my vector function, remember, is a vector. And this is the precise vector that I get here. The funny part is that actually, while this is a Calc 3 question, the Calc 3 portion of it was literally just knowing to take the limit of each of the pieces. But the rest of the work was completely Calc 1. Okay, let's take a look here at part B. Is this function continuous at the number 1? Okay, well, in order to figure that out, I would need to go ahead and actually check the definition for continuity. Okay, so I'll state here that we need to see if the limit as t approaches 1 of r of t is equal to r of 1. I'll even put a little question mark over there because that's what I'm attempting to see. Are both of those sides equal? Well, fortunately, we already calculated the left side, and that's 1, 3, negative pi as a vector. So we already know that. What is r of 1? Well, let's go back and see. I'll go ahead and just say, note that r of 1 is going to be equal to a vector. And let's just plug in 1 here and see what we come up with. Notice again that the middle component is still going to be 3, but I can't really plug 1 into the first component, right? If I just try to directly plug 1 in, I get 0 divided by 0, which is nonsensical, right? Like, I can't do this. This is just nothing. And similarly, if I try to plug in 1 here, I get absolutely nothing. So what I'm going to say here, this is undefined. Well, if it's undefined, then of course it's not equal to 1, 3, negative pi, that vector. So my limit of r of t as t approached 1 is most certainly not equal to r of 1. This means that r of t is not continuous, oops, not at x equals 1, but at t equals 1. Okay, so I was able to go ahead here and demonstrate continuity at a specific point by going back and using the definition. You'll need to make sure that you understand how to do this in case you were asked a similar style question. Of course, if you happen to have any questions over how we actually go back and do any sort of these computations, or you're concerned about anything you're seeing in the worksheets, feel free to let me know. In the next video, we're going to go ahead and try to take the concepts that we've talked about here in terms of calculating limits and see how we might be able to extend that now into the notion of taking the derivative of a vector valued function.